Hello, in this video I'm going to go over section 10.1 in our book, 3D Coordinate System. Now, before I do that, I want to make sure to review what we know so far from previous math classes. So when we say 1D, it's one dimension. The notation will be this fancy R, which is the real numbers. And here, what we're talking about is just the real numbers, right? You can think about it like the x-axis, where you have your -1, 0, 1, and so on. Now in 2D, we're going to use R squared, which means I am literally copying the x-axis. So now I have my x-axis, and then I make a copy of it, and now I have the y-axis. And this is what we know, right? We know how to deal with the Cartesian system. So since I'm copying this, if this is 1 and 2 and -1 and -2, 0 is here, then y will be 1, 2, -1, -2, right? Just like we know. You can actually define this using sets. So this is going to be the set of all order pair of 2, such that both x and y are elements of the real numbers. This epsilon here represents in, okay? Now in 3D, that's what we have to decide, but at least we know that 3D, the notation will be, now I'm making a third copy of the x-axis, so this is R3, and we're going to represent these points using ordered pairs, but now we're going to have triples, okay? And it's ordered because we're going to have that this is, the first component represents the x value, the second component will be y, and then the third component represents the location in terms of z, okay? We're going to define the point 0, 0, 0, like I'm 0 units away from any of the axes as the origin, right? Like in 2D, that would be 0, 0, right? And in 3D, I'm going to let 0, 0, 0 be the origin. Now, if I continue to do this, if I say, okay, then this is going to be, if I keep going like this, then this is x larger than 0, and this would be x less than 0. And if I continue by adding here my negative part of the y-axis, this is y larger than 0, and this would be y less than 0. And same thing happens if I let z go. So this is z larger than 0, z is less than 0. It's like, imagine, it's like saying the xy plane, it's down here. It's like it's the floor, and then the z-axis represents like the height. This is like coming out of the floor, okay? Now, the problem here is that how do you decide what is x, y, and z, right? By convention, we always say that this is x and this is y. But now we have a third axis. So in this class, and usually what we do is we follow the right-hand rule. So what that says is that whatever I decide, whatever I make my x-axis, I'm going to like close my hand and move in the right, right? I'm going to close my hand, like my right hand, and I'm going to go in this direction, okay? Now, in this case, a little bit more than that, it ends up being that if I put the palm of my hand here, and I put my fingers here, then my thumb will be pointing up, okay? So the right-hand rule tells me that if this is x, then this is y, this is z, which I'm going to stick to that, but it could be like if I make this x, then I have to continue with that movement, making this y and then z. And then if I make this x, then I continue with my moving in that direction, then this is x, this is y, this is z. So for now, this what I just said about placing your palm here and then your fingers here and having your thumb pointing up, it's not so important, but it become very important when we talk about the cross product, okay? Which we don't know yet, so this is all you need for now. Okay, so let's start understanding this. Let me tell you one thing, which is I am not good at drawing anything. So what I'm going to do is I'll do my best, which is going to be really bad, and then I'll show you these things in Desmos, okay? I'll give you the link and everything so that you can play around with these things. But long story short, if I'm in 2D, imagine for a second, if I'm in 2D and I only had the point 2, 3, right? The point 2, 3 in 2D, This would be, well, this is 2, this is 3. This means I'm moving 2 units away from the y-axis. So I'm moving 2 units in the direction of x, and then I'm moving 3 units in the direction of y. So this would be the point 2, 3. Now it takes a little bit of time to get used to this, but now this is my xy plane, okay? This is my xy plane. So if I move 2 units away in the direction of x and 3 units away from the center in the direction of y, the point 2, 3 will be on the floor, right? It will be on the floor. Now, if I want to have this point, the point 2, 3, 4, then I need to take this point that's on the floor and move it up 3 units. So let me show you what I mean. Not 3, but 4. So here we have 4. So this is what we're doing. I'm moving 2 units in the direction of x. Then I'm moving 3 units in the direction of y. And then I have to move 4 units in the direction of z. Okay, so this will be the point 2, 3, 4. Okay, now too bad. Now, the idea of this video, it's like to extend everything that we know in 2D, extend it to 3D. So for example, in 2D, if I have a line, let's say, for example, if I have let me just do x equals 3. So if I have x equals 3, I know that y is free. So then x equals 3 will be just a vertical line going through x equal to 3, meaning x is always 3 and y could be anything. So if I were to expand this to our 3D system, right, then this is x, this is y. If I expand this to the 3D system, then I would have x equal to 3 will be parallel to the y-axis. So this is still, we put 3 here, this is still there, right? And then it will be parallel to the y-axis, so something like this. And this is still happening, let me make it here. This is still happening on the xy plane. Now, the moment I want to move this up to 3D, then it turns into a plane. So a line in 2D, if I want to extend it to 3D, now it'll turn into a plane. What plane? Imagine I take this line and I sort of pull it like turn it into like a sheet of paper, okay? So then if I take it and I pull it up and down, it's infinite when it comes to z and actually y. Then this is going to be parallel to the z-axis, okay? So let me make it here, something like this. It is parallel to the z-axis. And then again, it's not going to be great because, yeah, I'm not great at drawing this, but I'll show you in a minute what this actually looks like. Okay, I'll draw some other stuff and then I'll show you. Now, again, I'm going to keep comparing 2D to 3D because it's the natural way to understand this. So if I'm in 2D, so 2D, we know that this is x and this is y. It's only one plane. I have the xy plane. And I also know that this is the first quadrant when both x and y are positive, and this is the second quadrant where x is negative and y is positive, and so on. But now that I add a third axis, now I split this into 8 different regions. It's octants, right? Not quadrants anymore, but octants. Let me just write it, octants. But nobody actually cares which one is which, okay? So here we have quadrants. But what we actually, at least we need to understand, even though I'm not going to force you to learn which one is which, but you could guess like the octant where they're all positive, that'll be your first one and so on. But let me just like look at this real quick. So I color coded this. Let me start with the blue one. So if you look at the blue one, it's when z is equal to 0, right? So this is the blue one. Z is equal to 0, that would be the xy plane. So let's say blue, it's when z is equal to 0. This is the xy plane, okay? Let me look at the orange one. So if I look at the orange one, you'll see that the orange one, there's a relationship between x and z. So if I'm related x and z, then that means that y is equal to 0. Therefore, this is the xz plane. So orange, it's when y is equal to 0. Therefore, this is the xz plane. And then finally, I have the purple one, and the purple one, it's when you have a relationship between y and z, right? So there's a relationship between y and z, therefore x is equal to 0. So the purple one, it's when x is equal to 0, so this is the yz plane, okay? Okay. All right, perfect. Let's try some more stuff. Let's do more examples, see if we understand this. We understand how to extend these things, okay? Then one more time, y equals 3 minus x. We know it's a line, okay? In 2D, this will be a line. And this is the line, let's see. So this is a line, okay? And when x, this is y. When x is equal to 0, I get y equals to 3. And when y is equal to 0, I get x equals to 3. So this is it. This is the line. This is the line y equals 3 minus x. Now, same thing that happened before is going to happen here. What's going to happen is that in 3D, this is x, this is y, this is z. I still have the same line on the xy plane. So this is 3 and this is 3, and I still have the same line. I still have the same line, but now if I'm in 3D, I can extend it to 3D by pulling my line and turning it into a sheet of paper. Like, that's the way I like to think about it, right? So this is going to be, let me see, a little plane. Let me make sure that I keep the slope, right? Because it'll be a plane, but it'll be slanted. It'll have that slope, right, in the direction of the XY plane, okay? Perfect. So still not doing great with my drawings. I think this is going to be better for me because if I have z equal to 3, it means that both x and y are free. So if I'm doing this in 3D, and this is x and this is y and this is z, and then I don't know why, but usually we just draw the positive ones, and then if we need the negative ones, then we just add them. So we always just draw the positive part of our axis, but then you also know that there's a negative part to them. Okay, so long story short, if I'm doing z equals 3, it's like I take my xy plane, and I'm going to move it up 3 units. So if this is 3, it's like, again, I take my xy plane and I move it up 3 units. So I'm here, now 3 units. Okay? So maybe, let me try one more time. Like I keep trying. Okay, let's do this. Maybe if I put it here, so you see it's like, okay, all right, something like that, okay? So this is, it's like saying the XY plane up 3 units, okay? Move it up 3 units. Perfect, okay. What does x from -1 to 3 represent? Okay, so then again, we do this in 2D first. So if I'm thinking about this in 2D, and it's very important to understand how to go from like 2D to 3D, because we're going to use this a whole lot, okay? So if I were doing this in 2D, then x would be in between -1 and 3, okay? So the value of x is restricted by -1 and 3, okay? But then y can be anything. So if y can be anything, then it's like we have this little rectangle, okay? So this would be x from -1 to 3 in 2D. Now, if I expand this to 3D, then hopefully you see that what's going to happen now is that I start with my little, let's say, rectangle. So then again, let me take the negative part. So -1, 3, okay? And then y can be anything, okay? Y can be anything. So this is, let's see. This is something like this. This is 1. So it's going to be here from -1 to 3, and then y can be anything, okay? Y can be anything. So this is what we had in 2D, but now in 3D, imagine I take this rectangle and then I move it up. So I'll get a 3-dimensional figure now. So then let's see. So it's something like this. Okay, and then here, and then here, and then here, and then here, and so on. Okay, and then here. Okay, and then am I missing? I feel like I'm missing something. Okay. Okay, I'll show you in a minute. I'll show you. And then it goes down. I'm not going to even try. All right, what else do we have here? That looks better. I feel like I can do better. Hold on. I hope you're able to like visualize this. I feel this is what I was saying. I suggest you play around with these things, okay, to sort of see what they look like. Okay, not too bad. All right, perfect. Now, if I look at x squared plus z squared equal to 64, again, I'm going to go back to 2D because that's what we know. So 2D, if I gave you x squared plus y squared equal to 64, easy, right? This would be a circle of radius 8. Let me change the color. That's boring. Let me make it pink. This would be a circle of radius 8 center at 0, 0. Not a problem. But now I don't have y. I have z. I have z. So let's move on. Let's move up to 3 dimensions. Okay. So I have here my x, y, and z. So if I have x squared plus z squared, then y is equal to 0. So this is actually centered. This is actually happening on the xz plane. On the xz plane, okay? So this would be, this is when y is equal to 0. So let me make it here. Okay. Now, since y is free, then this turns into a cylinder, okay? A cylinder on the y-axis. So imagine I put this here, so it'll be something like this. Let me see. Okay? It's an infinite cylinder, but I'm putting that so that you sort of imagine what's happening, okay? Look at that. All right, so this is this like, let's say this, if you were to look at it from the front, right? If you were to look at this from the front, then this is the xz plane, okay? All right, and this is happening along the y-axis. So now we have two different things here. We have x squared plus z squared is exactly equal to 64. That'll give you just the boundary, like the shell, the exterior, okay? So this will be the boundary. If we had x squared plus z squared less than 64, this would be the interior of the cylinder. And then if I give you less than or equal to 64, like in this case, this gives you both the interior and the shell, the boundary of that cylinder, okay? So this is both. Okay. All right, now we have to find formulas for the distance and the midpoint between 2 points now that we are in 3D. Now, let me remind you of what these formulas are in 1D and 2D. In 1D, I just have x1 and x2. If I want to know what the distance between them is, it's just this, okay? In 1 dimensions, this is just distance is equal to the absolute value of x2 minus x1, which is the same as the absolute value of x1 minus x2, okay? Now, if I'm in 2D and I have my 2 points, let's see, I have this point here and this point here. I'm going to call my first point P, x1, y1, and then let me say Q instead, Q, x2, y2. Then the distance between the 2 points, it's equal to this, D, which we know that I can complete a right triangle and use the P theorem, Pythagorean theorem. Okay, now if this is the point x1, y1, and this is the point x2, y2, then this right here will be the point, this will be the point x1, and the thing changing here is y. So this will be the point, the x at the same level and the y is at the same level. So this will be x1, y2, okay? That means that the distance from this point to this point, the only thing changing is y. So this would be the absolute value of y2 minus y1. And this length here will be the distance between this point to this point. The only thing changing here is x. So this would be x squared minus x2 minus x1. Using the theorem, then we know that d squared is equal to, I'm going to get rid of the absolute values because I'm going to square it. So x squared minus x1 plus y squared minus y1. And then I can take the square root. So this would be x squared minus x1 squared plus y squared minus y1 squared, okay? You know that when you take the square root, in theory, you take the square root, you get plus minus. But it's distant, so I'm going to keep it positive. Now in 3D, it's going to be interesting how at the end of the day, we end up getting a formula that makes so much sense, but the actual proof is not so trivial, okay? So long story short, I'm going to have my point here. This is going to be, I'm going to say this is P, and it has coordinates x1, y1, and then z1, and this is the point Q with coordinates, let's say x squared, not x squared, but x2, y2, z2, and I'm looking for the distance. Now, what I'm going to do is, this is D. What I'm going to do is, to make this easier for me, I'm going to make those 2 points, they're going to be part of a box. So this is what I mean. What I'm going to do is, this is x, this is y, this is z. I'm going to draw a little box first, and then I'll put the points, because otherwise I'll be lost. So this is what's going to happen. So I have here a little box, okay, and then a little box. Doesn't have to be perfect, okay. And then I'm going to connect this so that it looks like a little box. And what I'm going to do is, I'm going to assume that this is my point P, this is the x1, y1, z1, and this is going to be Q. So what's happening here is that P, which is x1, y1, z1, this is the back left corner of the box, and then Q, which is x2, y2, x2, y2, z2, it's going to be in the front in the right corner, okay? So I'm looking for this distance. Oh God. So this is 3D, right? So I'm looking for that distance. Okay, so again, feel free to skip this proof if you're not interested. But what I'm going to do is, I'm going to compute a couple of distances, right? So I need this length, okay? So I know that if I need this length, I can complete here a triangle. And then this is going to be the hypotenuse of that triangle, okay? So let me make it, let me use colors for this. So this is one triangle, okay? So I need this second length, which is the hypotenuse of this other triangle, okay? So let's see. Okay. So let's see. Okay, so this is, let's see what these points are. So these points, it's the x, the y and z components are the same. The only thing changing here is x, right? It's changing in that direction. So this point right here is the point, it's the point x2, y1, z1, and then, okay, perfect. And then this point right here is the point, well, I am changing y, right? But z is in the same, it's the same level in the z direction, and then what else? And then x is the same. So the only thing changing here is the value of, so this is going to be this point over here, is the point x2, right? Because it's in the front, so this is x2, and then y2, because it changed from y1 to y2, and then it's z1 because it's on the floor. You can think about it like on the floor, okay? I think that's enough for me to be able to compute this. Let's see. So that means that this length right here, the only thing changing is x. So this right here, maybe let me use black. So this length this right here is going to be x2 minus x1. And then this one, the only thing changing here is the value of y. The only thing changing here is the value of y. So this is going to be the absolute value of y2 minus y1. So that tells me then that the hypotenuse, I'm going to call it C, whatever. I'm going to call it C. So the hypotenuse C, okay, that's ugly. Maybe go back to black. C right here, C squared is equal to, well, I take the sides, square them, and add them together. So this is x squared minus x1 squared plus y, not squared, but x2 minus x1 squared plus y2 minus y1 squared. Okay, perfect. So I know what c squared is, not a problem. Now, if I look at this, let me call this E, then I know that D squared is equal to C squared plus E squared, okay? But E, the only thing changing here is the value of Z. So E is equal to the absolute value of Z2 minus Z1. Therefore, D squared is equal to C squared, which is x2 minus x1 squared plus y2 minus y1 squared. I'm getting rid of the absolute values because I'm squaring the quantities, plus E squared, but E is equal to the change in Z. So plus Z2 minus Z1 squared. Final answer, D is just equal to what we thought it would be, right, if we had to guess, which is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Perfection. All right. So that tells me then that this is going to be the formula for distance in 3D, okay? This is going to be the formula for distance in 3D. I'm just going to take it with me. Okay. Perfect. So long story short, I'm going to just use a notation. I'm going to say the distance. So let P be equal to x1, y1, z1, and Q is the point x2, y2, z2. Then the distance between P and Q, 2 points in R3, it's given by, and then the distance formula. That's ugly. I'm just going to write it again. So it'll be the square root of x2 minus x1 squared plus y2 minus 1 squared plus z2 minus z1 squared, okay? Now for the midpoint, we know how to compute the midpoint. Again, it'll be exactly the same thing. So it'll be the midpoint of each of the components. So in 1D, we know that if this is x1 and this is x2, right, then the midpoint, I'm going to call it M, it's equal to x1 plus x2 divided by 2. And in 2D, you do it for x and y. Therefore, in 3D, the midpoint between P and Q, it's equal to, you take the midpoint of each of the components. So x1 plus x2 divided by 2, y1 plus y2 divided by 2, z1 plus z2 divided by 2. Okay, let's do some examples. So what is the distance between -1, 2, 4, and 1, -2, -3? So using the formula, I know that this is going to be, I'm going to say this is x1, y1, z1, x2, y2, z2. Therefore, distance, it's equal to the square root of. I take the difference of each of the components and square them. So I'm going to do x2 minus x1. So x2 minus x1 squared plus, and then I do y2 minus y1. So y2 minus y1 squared plus, and then z2 -3 minus z1, so -3 minus 4, square it, and then simplify this. So this is 1 plus 1, you get 2 squared. So you get 2 squared plus, and then you get -2 minus 2, you get minus 4 squared plus, -3 minus 4, you get -7 squared. So root of 4 plus 16 plus 49. This is 20 plus 49. You get root of 69, okay? Perfect. And you don't have to write all these steps, okay? Feel free to skip anything you feel like skipping. Okay. What is the midpoint between -1, 2, 4 and 1, -2, -3? Well, we talked about it. You just take the midpoint of each of the component, right? Between the components of x, y, and z. So I'm going to write it. So it'll be, it's -1 plus 1 divided by 2, 2 minus 2 divided by 2, 4 plus -3 divided by 2, okay? So one more time, you add, right? So x1 plus x2 divided by 2, and then y1 plus y2 divided by 2, and then z1 plus z2 divided by 2. Simplify it, and you get literally the midpoint. 0, 0, and 1/2. Okay? Perfection. So now that we have defined the distance between 2 points, we can extend the idea of a circle to a sphere, okay? So in 2D, we have a circle, and we know that if I have a circle center at, this is the center HK, this is the center HK, and this is the radius R. Let me use like colors for this. R. Then a circle is the set of points X, Y, so in 2D, such that the points are distance away from the center. So the equation of a circle, it's going to be equal to the set of x, y's such that x minus h squared plus y minus k squared is equal to r squared, okay? And in 3D, it'll be exactly the same thing. So it's the set, I'm going to say set of points x, y, z, distance r from the center, let me say from the center, which we're going to say is h, k, l, okay? So then this is going to be, I have my sphere here. This is x, this is y, this is z. I draw it here, something like that. And then I like to do this so that you see it's a three-dimensional figure. And then if this is the center, let me be consistent with the circle, then this is going to be r, okay? And the formula is going to be, we know the formula for distance in 3D, okay? So it'll be the set of x, y, z's that are our distance r from the center, okay? So it's exactly what we have. So x minus h squared plus y minus k squared plus, now I have the z component equal to r squared. So let me give you the formal definition, which is what we just did. Okay, I don't think I actually have to write it. So I'm just going to say this is the equation. Equation of the circle is, I'm going to say Equation of a circle is set of points x, y, z in R3, obviously, such that x minus h squared plus y minus k squared plus z minus k squared is equal to r squared, okay? Perfection. So I already recorded a little video. You can click on this once I post the blank notes, reminding you of how to complete the square and how to get to the equation of a circle or a sphere. This is a little harder example, so I'm just going to do it real quick, okay? Now, the first thing you have to do, you have to make sure that the coefficient of x squared, y squared, and z squared, the coefficient has to be 1. Okay, so it's a good thing that we have exactly the same coefficient because we have to divide everything by that. So step 1, divide everything by 2. One more time, the reason why we're doing that is because I need the coefficient of x squared, y squared, and z squared to be 1. So I get x squared plus y squared plus z squared is equal to 6x minus 8z plus 1/2, okay? Perfect. Step 2, oh, that got really thick. So step 2, I have to complete the square, okay? And then to complete squares, what we're going to do is we're going to add the coefficient of the linear term divided by 2, okay, and squared it. So let me show you. So what I'm saying is that I have x squared minus 6x. I have to add whatever completes that squared plus y squared. There's no linear term for y, so I have to add something to make it a perfect square, and then plus z squared plus 8z plus whatever makes that a perfect square, and then you keep the 1/2 on the right hand side plus whatever you have to add to complete all the squares, okay? So let's do one at a time. So here I have to do, it's -6 divided by 2 squared, so this is -3 squared. Keep in mind that this -3, it's what's going to be when you do, that's what you're going to write when you do x minus something squared, okay? So I have -3, so if I have -3 there, I have to write -3 here to keep the equation going. Then for y squared, well, there's nothing, right? There's nothing. So this is already a perfect square. So I'll just add 0 for y. I'm just sticking to the algorithm. And now for z, I do a divided by 2 squared. I get 4 squared, so I get 16 and 16. So if I simplify this, I'm going to get my perfect square for x. It's going to be x minus 3 squared. And you can double check, right? You get x squared minus 6x plus 9. Perfect. That makes sense. That makes sense. Oh, see, this is why you have to check your work. This should be a 9. This should be a 9. If I add 9 here, I have to add 9 here. Oh, good call. Perfect. So it's going to be x minus 3 squared. Perfect. And then I keep simplifying this. I get plus y squared. And then I get plus, and this is z plus 4 squared. And then we check. We get z squared plus 8z plus 16. Beautiful. And this is equal to, and I simplify the right-hand side. What do I get? I get 16 plus 9. 16 plus 9 is 25. So I have to do this. I get 1/2 plus 25. So this is equal to 16, 25, right? Yes. 2 times 25, I got, what do I get? 50? 2 times 25, I get 50 plus 1, I get 51 divided by 2. So 51 divided by 2 is what I get on the right-hand side. And then from here, I know what the center and radius are, okay? And the radius. So center is 3, 0, -4, and then the radius is the square root of that whole thing, okay? So root of 51 divided by 2. All right. So what is the set of points x, y, z such that x minus 1 squared plus y plus 2 squared plus z minus 3 squared less than or equal to 4? So in other words, we have to describe this. What is this? So we see that this is the left-hand side of the equation of a sphere. And then if we had the equal sign, it would be just the sphere of radius root of whatever I have on the right-hand side. But we have less or equal to, so this tells me that it will be the interior as well as the boundary, okay? So this is the interior. And I'm going to say boundary of a sphere of radius 2 centered at 1, -2, 3. Keep in mind that the formula has negative. So if I have here, if I'm adding, I have to think about it like y minus -2. So the y component of the center, it's actually -2. I have one more example and then I'll call it a day. So find an equation of a sphere if one of its diameters has endpoints 0, 4, 4 and 4, 8, 8. Okay. So we know that, what do we know? We know that the radius, so I'm going to say, first of all, radius is half the diameter, okay? So that means that it's just, if you think about it, the diameter is the distance between the 2 points, and I want half of that, so I'm just looking for the midpoint, okay? Does that make sense? So let's see. So radius is half the diameter. So I know that I just have to find the distance between the 2 points and divide it by 2. So let's see. So the distance, so diameter, it's equal to the distance from 044 to 488, okay? This is equal to root of, and then we go change in x, so 4 minus 0 and square it, and then 8 minus 4 and square it, and then 8 minus 4 and square it. So I get that this is equal to 16 plus 16 plus 16 equal to 3 times 16, which is root of 16 is 4, so I get 4 root of 3. Since this is a diameter, then I know that the radius of this sphere has to be equal to the diameter divided by 2, which is equal to 4 root of 3 divided by 2 to root 3, okay? And then we know that the center must be, so diameter goes from, right? So if I have, even if it's a circle, the diameter goes from one side to the circle to the other side of the circle, right? Therefore, the center will be the midpoint, okay? So the center will be the midpoint. So I'm going to say it's the midpoint. So I'm going to say it's equal to the midpoint of 044 and 488. And this is equal to, and we know how it works, we just find the midpoint of each of the x, y, and z components. So this is equal to, I add the x components and divide them by 2. So 4 plus 0 divided by 2. Then I add the y components and divide them by 2. A plus 4 divided by 2. And then I add the z components and divide them by 2. This should be a 4 divided by 2. So I get that this is 4 divided by 2, I get 2. A plus 4 divided by 2, I get 12 divided by 2, which is 6. And then I do it again, and I get 6 again. So I have the radius, I have the center, I can find the equation of this sphere. So let me put it here, maybe pink for no reason. So that means that the equation of the sphere is, well, x minus, what is the x component of the center? it'll be 2, so x minus 2. X minus 2 squared plus y minus 6 squared, this is the center, right? Plus z minus 6 squared, it's equal to the radius squared. So it'll be, so radius squared, it's equal to 2 root of 3 squared. So I'm just going to write it as 2 squared, which is 4, times root of 3 squared, which is 3, you get 12. Maybe put it in, I'll do it in 2 steps. So 2 root of 3 squared, which is equal to 4 times 3, which is 12, okay? So it's just 12. Perfection. Okay. Now, what if I, just for fun, what if I want to find the intersection, if it exists, with any of the main planes, okay? So let's say intersection. How do I find the intersection? So intersection with, I'm going to say the xy plane. If I want the intersection with the xy plane, then this is when, don't forget, z is equal to 0. So if z is equal to 0, I go to here, right? And I make z equal to 0. So that means that, I'm going to go back to blue. So x minus 2 squared plus y minus 2 squared plus 0 minus 6 squared is equal to 12. Let's see if that gives me something that makes sense. So this gives me x minus 2 squared plus y minus 2 squared, it's equal to, or maybe do it in one more step, plus 36, it's equal to 12. X minus 2 squared plus y minus 2 squared, it's equal to 12 minus 36. X minus 2 squared plus y minus 2 squared, it's equal to negative 24. Impossible, right? You cannot have the sum of two squares being equal to negative 4. That means that there's no intersection. This sphere does not intersect the xy plane, okay? But maybe, let's see, maybe we can try something else, maybe with the yz plane. Let's see what happens if I try with the yz plane. So yz plane, so for the yz plane, we know that x is equal to 0. So let's see, back to blue. Let's see. So I do 0 minus 2 squared plus y minus 2 squared plus z minus 6 squared, it's equal to 12. So I get 4 plus y minus 2, that's a 2, not a z, 2 squared plus z minus 6 squared, it's equal to 12. So y minus 2 squared plus z minus 6 squared, it's equal to 12 minus 4, which is 8, okay? So what is this? This is it's the intersection of the sphere with the yz plane. So the intersection of the sphere with the yz plane is just a circle. It's a circle on the yz plane centered at 2, 6 with radius root of 8, okay? I hope this makes sense. Bye-bye.